An aquatic mechanical design presentation. This video segment shall explain the process for determining a pumping system's total dynamic head values, or as it is referred to, the TDH calculations. This presentation considers the following Public Swimming Pool Code guidelines: California Code of Regulations, Title 22, Division 4, Environmental Health, Chapter 20, Public Swimming Pools; California Building Code, Title 24, Public Swimming Pools, Division 1 and 2, Section 3100B; and NSF ANSI 50. Planning for system hydraulics and arriving at the design flow's TDH operational condition values, as it is defined by the code, shall involve analyzing the arithmetic difference between total discharge head and suction head. TDH is taking into account friction losses in the piping system's components under a prescribed design flow condition. Yet some interpret a pump's output as total dynamic head, although this is incorrect, and this misnomer is widely applied to the measurement for a pump's head-foot output. While it is true that the pump's head-foot measurement relates to the selected pump's ability to overcome the system's TDH hydraulic head loss conditions, the use of this shortcut terminology may lead to confusion for what a TDH analysis actually involves. In planning for a system's total dynamic head values and ultimate hydraulic analysis, it can be easy to misunderstand how to best prepare a set of plans, especially when employing terms that come from a branch of mathematics that are dealing with the properties and manipulation of numbers. Accounting for friction losses starts with determining the elevation difference from the water surface to the center line of a pump. This is to be measured in vertical feet. When the water is not in motion, it is referred to as static suction lift, which accounts only for the vertical distance in elevation feet between the center line of the pump and the water's surface level. The other portion of the static relationship is the static discharge head, which involves the elevation between the center line of the pump and the water level where the water is being pumped to. These two elevation considerations combined will equal the total discharge head, which can be both a positive head as well as a negative head contributing factor. In many swimming pool installations, the gains or losses from static suction lift and static discharge head are negligible, but when making determinations for the overall TDH, this will be one of several factors to be aware of. It can be a bit confusing when manufacturers imply on a pump curve that head feet is actually total dynamic head, but a pump's pressure output is not TDH, but a measurement of only head feet. And here is how calculating the total dynamic head actually works. Pumps do two things. They produce pressure, referenced as either PSI or head feet, and they suck and push water, but not both at peak performance output at the same time. A pump's impeller is designed to provide the benefits of a specific head-foot measurement of pressure and a specific GPM flow criteria. If the piping system with all its interrelated components such as elbows, T's, valves, etc. pose too much restriction, well then, the pool's impeller will provide more pressure than flow. This restriction is referred to as hydraulic head loss, or HHL. When the water in the piping system begins moving through the piping network, then hydraulic head losses or friction loss characteristics can be calculated at a design flow rate. The suction lift and discharge head, together with all quantified individual fittings, each length of pipe according to size, valves, equipment components, etc., are all totaled as a hydraulic head evaluation, and that accumulative total is what constitutes total dynamic head, or the TDH analysis. Section 3128B addresses all types of filters and prescribes the applicable requirements for each that has been established by the NSF ANSI Performance Standard, effective September 2012. Section 3128B calls out the allowable filtration rate per square foot of filtering area for each different type of filter, and Section 3126B calls out the recirculation pump capacity. As an example, the pumping capacity requirement for a high-rate sand filter must have a pump that can provide at least 60 head feet in order to be able to overcome the plumbing system's hydraulic head losses and still being able to deliver the required minimum filtration flow rate. Section 3126B.2 allows for the selection of other pumps that don't meet the 60 head feet capacity, provided that the turnover times can be maintained according to Section 3124B. In this example, we have a 21,500 gallon swimming pool and a pumping capacity of 61 head feet at 60 gallons per minute in order to accomplish the 6-hour turnover rate. In another example, we have a 1,650 gallon spa and a pumping capacity of 52 head feet at 55 gallons per minute in order to accomplish the 30-minute turnover rate. Thus, the conclusion is in both cases the pumping capacity is met according to both Section 3126B.2 and 3128B. Section 3126B.1, item number 4, indicates that a recirculation pump capacity for a high-rate sand filter must be at least 60 head feet. In the next two slides, Figure 1 shows diagrammatically the high-rate permanent media filter, and Figure 2 shows a conventional sand filter operating at an accelerated flow rate. Here are two primary differences between a high rate and a rapid rate sand filter, and the key difference in application is the flow capability per square foot of filtering area. Another important difference is the head foot output requirement for the recirculation pump's capacity. The code indicates that a high rate sand filter's pump needs to provide at least 60 head feet. The pump's ability to produce pressure is termed head feet. Total dynamic head, as the pump curve indicates here, isn't how TDH is calculated. TDH is calculated from all the total hydraulic head losses in the plumbing system that are arrived at when considering the following. A. The design flow rate necessary to accomplish the required turnover rate. B. The suction and discharge head lift due to any elevation differences. C. The velocity of water traveling through a variety of pipe sizes, maximum flow 6 feet per second for suction, 8 feet per second for the returns. And D. The hydraulic head losses that will occur in fittings, valves, equipment, components, etc. In tallying all these contributions, you will arrive at the total value for the TDH analysis. The purpose of this analysis is to make sure that the recirculation pump's capacity has ample pressure producing capability at the required flow rate. The 60 head foot threshold accomplishment can sometimes be required when a system's design calls for pumping water over further distances and or has more fittings and equipment component head losses. In arriving at the total for all the system's head losses, a corresponding result is seen for what GPM can be expected from the pump and whether or not it shall be capable of delivering the design flow requirement as specified. The objective here is to balance the GPM hydraulic capability with the head feet pressure capability and reach an equilibrium that can deliver the design flow rate while allowing the pump to operate within its best electrical energy efficiency range. Besides the pumping curve that involves the movement of water, there is another curve that indicates how the pump's motor performs under these varying conditions. We will address these conditions and the effects on electrical energy efficiency by the pump motor in our next video segment. In the meantime, I'm hopeful that this introduction can help you to better understand TDH analysis. And thank you for viewing.